The National Electrical Code sets limits on the number of conductors allowed in a conduit to ensure safety and prevent electrical hazards. The answer is correct in that you cannot put 4 number 12 THHN and 3 number 10 THHN in 1/2-inch EMT. According to the National Electrical Code, the maximum number of THHN conductors that can fit in a 1/2-inch EMT conduit is firstly 4 number 14 THHN, secondly 3 number 12 THHN, and thirdly 2 number 10 THHN. Adding 3 number 10 THHN to the existing 4 number 12 THHN exceeds the NEC limit. There are several reasons for the limit. The first reason is heat dissipation. Overcrowding conductors in a conduit can create excessive heat, which can damage the insulation and lead to electrical hazards. The second reason is wire movement. Conductors need space to move freely to accommodate thermal expansion and contraction without damaging each other. The third reason is pulling force. Attempting to pull too many conductors through a conduit can be difficult and could damage the wiring. There are consequences of exceeding the limit. Firstly, code violation. Installing more conductors than allowed by the NEC is a code violation. Secondly, fire hazard. Overheating due to overcrowding can increase the risk of electrical fires. Thirdly, system failure. Insufficient wire movement can cause conductors to become jammed and fail to operate properly. Therefore, it is important to adhere to the NEC guidelines for conduit fill to ensure safety and reliability. When determining conduit fill, several factors must be considered. Firstly, the size and type of conduit. Different sizes and types of conduit, such as ENT, rigid metal conduit, and PVC conduit, have different fill capacities. Secondly, the size and type of conductors. The size and type of conductors, such as THHN, THWN, and XHHW, affect the amount of space they occupy in the conduit. Thirdly, the number of conductors. The total number of conductors in the conduit must be within the allowable fill percentage. The NEC provides tables and guidelines for calculating conduit fill. These tables specify the maximum number of conductors of a given size and type that can be installed in a particular size and type of conduit. To calculate conduit fill, firstly determine the cross-sectional area of each conductor. This information can be found in NEC Chapter 9, Table 5 and Table 5a. Secondly, add up the cross-sectional areas of all the conductors. Thirdly, determine the inside area of the conduit. This information can be found in NEC Chapter 9, Table 4. Fourthly, calculate the percentage fill by dividing the total conductor area by the conduit area and multiplying by 100. The allowable fill percentage depends on the number of conductors in the conduit. For example, for 1 or 2 conductors, the maximum fill percentage is 40%. For more than 2 conductors, the maximum fill percentage is 40% for conduit 21 trade size and smaller, and 40% for conduit sizes larger than 21 trade size. It is important to note that these are general guidelines, and there may be exceptions or additional requirements in specific situations. Always consult the latest edition of the NEC and local codes for the most accurate and up-to-date information. In addition to the basic conduit fill requirements, there are also specific rules for dirting conductors when multiple conductors are installed in a conduit. Dirting is the process of reducing the ampacity of conductors to account for the heat generated by multiple current-carrying conductors in close proximity. When the number of current-carrying conductors in a conduit exceeds 3, the ampacity of the conductors must be derated according to NEC Table 310.15. The derating factors vary depending on the number of conductors and the insulation type. For example, if there are 4 to 6 current-carrying conductors in a conduit, the ampacity of the conductors must be derated to 80% of their normal ampacity. If there are 7 to 9 current-carrying conductors, the ampacity must be derated to 70%. It is important to apply these derating factors to ensure that the conductors are not overloaded and that the insulation does not overheat. In addition to conduit fill and derating, there are also requirements for the type of conductors that can be used in a conduit. The NEC specifies the types of insulation that are suitable for different applications. For example, THHN conductors are commonly used in dry locations, while THWN conductors are suitable for wet locations. It is important to select the appropriate type of conductor for the environment in which it will be installed. The NEC also provides guidelines for the installation of conductors and conduits. These guidelines cover topics such as bending radius, support spacing, and the use of pulling compounds. The bending radius of a conduit is the minimum radius to which the conduit can be bent without damaging it. The NEC specifies minimum bending radii for different types of conduit. The support spacing is the maximum distance between supports for the conduit. The NEC specifies maximum support spacings for different types of conduit and conductor sizes. Pulling compounds are lubricants that can be used to reduce friction when pulling conductors through a conduit. The NEC recommends the use of approved pulling compounds to prevent damage to the conductors and conduit. In summary, the National Electrical Code sets limits on the number of conductors allowed in a conduit to ensure safety and prevent electrical hazards. These limits are based on factors such as heat dissipation, wire movement, and pulling force. Exceeding these limits can result in code violations, fire hazards, and system failures. To determine conduit fill, you need to consider the size and type of conduit, the size and type of conductors, and the number of conductors. The NEC provides tables and guidelines for calculating conduit fill. In addition to conduit fill, there are also requirements for adhering conductors, selecting the appropriate type of conductors, and installing conductors and conduits. Always consult the latest edition of the NEC and local codes for the most accurate and up-to-date information. Always ensure there is sufficient spacing of conductors when pulling. Firstly, proper planning is essential for a successful conduit installation. Before starting the project, carefully plan the route of the conduit and determine the number and size of conductors that will be needed. Secondly, select the correct size and type of conduit. The conduit must be large enough to accommodate the conductors without exceeding the fill limit specified in the NEC. Thirdly, use the right tools and equipment. Use the appropriate tools for cutting, bending, and joining the conduit. Fourthly, properly support the conduit. Support the conduit at intervals specified in the NEC to prevent sagging or damage. Fifthly, pull conductors carefully. Use pulling compounds and techniques to avoid damaging the conductors during installation. Sixthly, make proper connections. Ensure that all electrical connections are made correctly and are properly tightened. Seventhly, inspect the installation. After the installation is complete, thoroughly inspect the conduit system to ensure that it meets all applicable codes and standards. Ignoring these rules can lead to unsafe installations. Firstly, never exceed conduit fill limits. Overfilling a conduit can lead to overheating and potential fire hazards. Secondly, avoid sharp bends. Sharp bends in the conduit can damage conductors and make it difficult to pull them through. Thirdly, do not mix different types of conductors in the same conduit. Mixing different types of conductors can lead to insulation damage and potential electrical problems. Fourthly, never use damaged conduit. Damaged conduit can compromise the integrity of the electrical system and create safety hazards. Fifthly, avoid overloading circuits. Overloading circuits can cause breakers to trip and can lead to overheating and potential fires. The NEC provides tables and guidelines for calculating conduit fill, adhering conductors, and selecting the appropriate types of conductors for different applications. These tables and guidelines are based on extensive research and testing, and they are designed to ensure the safety and reliability of electrical systems. Failure to comply with the NEC can result in fines, penalties, and potential liability in the event of an accident or injury. By following the NEC and other applicable codes and standards, electrical contractors can ensure that their installations are safe, reliable, and compliant. This can help to protect people and property from electrical hazards and can help to avoid costly mistakes and rework. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to check with local authorities to determine what codes and regulations are in effect in a particular area. Some local codes may be more stringent than the NEC, and it is important to comply with all applicable requirements. In conclusion, adhering to the NEC guidelines for conduit fill is essential for ensuring the safety and reliability of electrical systems. Overcrowding conductors in a conduit can lead to overheating, insulation damage, and potential fire hazards. By following the NEC and other applicable codes and standards, electrical contractors can help to protect people and property from electrical hazards and can help to avoid costly mistakes and rework. Remember to always consult the latest edition of the NEC and local codes for the most accurate and up-to-date information. Also, remember that different types of conduit have different fill capacities. Electrical metallic tubing, or IMT, is a thin-walled and threaded tubing commonly used for indoor electrical raceways. Rigid metal conduit, or RMC, is a thick-walled, threaded conduit typically used for outdoor or harsh environment applications. Intermediate metal conduit, or IMC, is a lighter-weight threaded conduit that can be used in place of RMC in some applications. PVC conduit is a non-metallic conduit made of polyvinyl chloride, commonly used for underground or corrosive environment applications. Each of these conduits have different fill capacities depending on their size. The fill capacity for EMT is defined in Article 358.22. The fill capacity for RNC is defined in Article 344.22. The fill capacity for IMC is defined in Article 342.22. The fill capacity for PVC is defined in Article 352.22. These articles all refer to Chapter 9, Table 1 for fill capacities. Understanding these differences is critical to safety.